Lesson 20.2, Independent Events. Essential question: what does it mean for two events to be independent? Let's see. Two events are independent provided the occurrence of one event has no effect on the occurrence of the other event. It's written probability of A given B equals the probability of A. Understanding the independence of events. Suppose you flip a coin and roll a number cube. You would expect the probability of getting heads on the coin to be 1/2, regardless of what number you get from rolling the number cube. Likewise, you would expect the probability of rolling a 3 on the number cube to be 1/6, regardless of the coin flip regardless of whether the coin flip results in heads or tails. When the occurrence of one event has no effect on the occurrence of another event, the events are said to be independent events. A jar contains 15 red marbles and 17 yellow marbles. You randomly draw a marble from the jar. Let R be the event that you get a red marble and Y be the event that you get a yellow marble. Since the jar has a total of, 15 and 17 is 32 marbles, the probability of getting a red would be 15 over 32, and the probability of getting getting a yellow would be 17 over 32. Suppose the first marble you draw is a red marble, and you put that marble back in the jar before randomly selecting a second marble. Find the probability of Y given R. The probability that you get the yellow marble on the second draw after getting a red marble on the first draw. Explain your reasoning. Since the jar has a total of 32 marbles and 17 of them are yellow, the probability of yellow given red would be 17 over 32. Suppose you don't put the red marble back in the jar after randomly selecting or randomly drawing a second marble. Find the probability that yellow given red, the probability that you get a yellow marble on the second draw after getting a red marble on the first draw. Explain your reasoning. Since the jar has a total of 31 marbles and 17 of them are yellow, it would be 17 over 31. Okay. Remember, it had 32, but you took a red one out, which made it 31. In case you replaced the first marble before drawing the second marble, in one case you replaced the first marble before drawing the second, and in the other case you didn't. For which case was the probability y given r equal the probability of y? Why? So let's see. The probability of y given r equals the probability of y when the red marble was replaced because the total number in the jar stayed the same. Okay, remember probability of yellow was 17 over 32. Probability of yellow given red would only be equal to that if after you drew the red, you put it back in the jar. In which of the two cases would you say the events of getting a red marble on the first draw and getting a yellow marble on the second draw are independent? What is true about the probability of y given r and probability of y in this case? The events are independent when the marble is returned to the jar. The events are independent when the red marble is returned to the jar. All right. Mathematically, you would write a probability of y given r equals the probability of y. Determining if events are independent. To determine the independence of two events A and B, you can check to see whether the probability of A given B equals A, probability of A, since the occurrence of event A is unaffected by the occurrence of event B if and only if the events are independent. The two-way frequency table gives data about 180 randomly selected flights that arrive at an airport. Use the table to answer the questions. So we'll let you do A on your own. Just go ahead and read it and follow along, and then we'll do B together. Is the event that a flight is international independent of the event that a flight arrives late? Let I be the event that a flight is international. Let L be the event that a flight arrives late. Find the probability of I and the probability of I given L. To find the probability of I, note that the total number of flights is 180, and of those flights, there are 60 international flights. So we have 60 over 180, which gives you 33 and a third percent. To find the probability that I given L, note that there are 18 flights that arrive late, and of those flights, there are 6 international flights. So the probability of I given L is 6 over 18, which is 33 and 1/3%. Since the probability of I given L equals the probability of I, the event that a flight is international, is independent of the event that a flight arrives late. All right, your turn. Use the two-way frequency table. The two-way frequency table gives data about 200 randomly selected apartments in the city. Use the table to answer the questions. Okay. All right. One bedroom, 2+ bedrooms, total. Okay, single occupant. Is the event that an apartment has a single occupant independent of the event that an apartment has one bedroom? Okay. So we'll let SO here be single occupant. And we'll let 1B here be a one bedroom apartment. So the probability of single occupant is going to be 76 over 200, which is about 38%. And the probability, the probability of single occupant given it's one bedroom, that's going to be 64 over, and there's a total of 91 bedrooms. And that's going to be about 71%. Since they're not equal, the events are not, let's see. Since the probability of single occupant is not equal to the probability of single occupant given it's one bedroom, they are not independent events. All right. Is the event that an apartment has two or more bedrooms independent of the event that apartment has multiple occupants? So we'll say this is multiple occupants. And this is two bedroom, and it means two or more. All right. Probability, the probability of two bedrooms is going to be 110 over 200. And it's about 55%. And then we want the probability of two bedrooms given that it is multiple occupancy. All right. Two bedrooms given multiple occupants, that's going to be 98 over, and there's a total of 110 of those, and that's going to be approximately 89%. And since those two are not equal, the events are not independent. Probability of two bedrooms is not equal to the probability of two bedrooms given multiple occupants. They are not independent events. All right, good. Explain 2. Finding the probability of independent events. From the definition of conditional probability, you know that the probability of A given B equals the probability of A intersection B divided by the probability of B for any events A and B. If those events happen to be independent, you can replace the probability of A given B with probability of A and get probability of A equals the probability of A intersection B divided by the probability of B. Solving the last equation for the probability of A intersection B gives the following results. Events A and B are independent if and only if the probability of A intersection B equals the probability of A times the probability of B. Find the specified probability. Okay, go ahead and read A and try to follow along, and then we'll do B together. All right. B, you spin the spinner shown 2 times. What is the probability that the spinner stops on an even number on the first spin followed by an odd number on the second spin? Okay. Let E be the event of getting an even number on the first spin. So let's see, how many even numbers? See, 12's even, 8's even, 6 is even. So there are probability of an even, that's going to be 3 over 8. Okay, 4, 8. All right. Because the first spin has no effect on the second spin, the probability of odd given an even is going to be, well, that would be 5 over 8. Since the events are independent, you can multiply their probabilities. The probability of E or even intersection odd equals the probability of E, which is 3/8, times the probability of odd, which is 5/8, and that gives you 15 over 64, which is about 23%. In part B, what is the probability that the spinner stops on an odd number on the first spin, followed by an even number on the second spin? What do you observe? What does this tell you? The probability of getting an odd number on the first spin, followed by an even number on the second spin, is going to be, let's see, probability of odd times probability of even. That's going to be 5/8 times 3/8, which is 15 over 64. This value is equal to the probability calculated in part B. Because the spins are independent of each other, changing the order of outcomes does not affect the overall probability. Because the events are independent, changing the order of events does not change the probability. Six, your turn. You spin a spinner with 4 red sections, 3 blue sections, 2 green sections, and 1 yellow section. If all of the sections are of equal size, what is the probability that the spinner stops on green first and blue second. Okay, so we'll say green, the probability of green will be, well, let's see, we have two green, right? And then let's see, how many are there total? 4, 7, 8, 9, 10. 2 over 10, which is 1/5. Okay. Because the first spin has no effect on the second spin, the probability of, let's see here, the probability of blue given green really is just the probability of blue, which is, there's how many blue? 3 over 10. Since the events are independent, you can multiply their probability. And let's see, so let's see, the probability, let's see here, if all, what is probability? Green, the probability of green, oh, I'm sorry, probability of blue, well, green, intersection, blue, probability of green, intersection, blue, equals the probability of green times the probability of blue. Green times the probability of blue, which equals 1/5 times 3/10. That's 3 over 50, which is about 6%. All right. A number cube has numbers 3, 5, 6, 8, 10, and 12 on its faces. You roll the number cube twice. What is the probability that you roll an odd number on both rolls? Okay. Let's see here. We'll say let O1 be the event of getting an odd number on the first roll. And let's see. So how many odd numbers are there? 1, 2, see, 1, 2, 3, 4, 5, 6. There's 6 total, and 2 are odd. So that's going to be 2 over 6, which is 1/3. What is the probability of an odd number on both? So the probability, and I don't know why I put L there, probability. The probability of O2 given O1. Okay, now these are independent, right? So what happens on the first roll does not matter. So that means that this is going to be the same as the probability of an odd on the second roll, which is again 1/3. Again, since the events are independent, the probability of odd on the first intersection odd on the second equals the probability of an odd on the first times the probability of an odd on the second, which is 1/3 times 1/3, which is 1/9. And that's about 11%. Okay, good. Showing that events are independent. So far, you have used the formula probability of A intersection B equals probability of A times probability of B. When you knew that the events A and B are independent, you can use the formula to determine whether the two events are independent. Determine if the events are independent. Okay, go ahead and read A, and when you get back, we'll do B together. Okay, so what we're doing here is we're proving that the two events are independent, because sometimes you don't really know, and the math can prove it for you. The two-way frequency table shows data for 60 randomly selected children at an elementary school. Determine whether a child who knows how to ride a bike and a child who knows how to swim are independent events. Okay, so knows how to ride a bike, doesn't know how to ride a bike, knows how to swim, doesn't know how to swim. Let B be the event that the child knows how to ride a bike. Let S be the event that a child knows how to swim. Okay. Find the probability of B, the probability of S, and the probability of B intersection S. The total number of children is 60. There are 45 children who know how to ride a bike. 45. So the probability of B is 45 over 60, which is 3/4. There are 40 children who know how to swim. 40 children know how to swim. So the probability of S is 40 over 60, which is 2/3. There are 30 children, 30, knows how to ride a bike and knows how to swim. So the probability of B intersection S is 30 over 60, which is 1/2. Okay, good. Compare the probability of B intersection S and the probability of B times the probability of S. So probability of B times the probability of S is 3/4 times 2/3. That's 3 times 2. That's 6. 12s. 6/12 is 1/2. Because the probability of B intersection S equals the probability of B times the probability of S. The events are independent. They are independent. Okay. So I guess you don't have to know how to ride a bike to swim, and you don't have to know how to swim to ride a bike. Your turn. A farmer wants to know if an insecticide is effective in preventing small insects called aphids from damaging tomato plants. The farmer experiments with 80 plants and records the results in the two-way frequency table. Determine whether a plant that was sprayed with insecticide and a plant that has aphids are independent events. Independent events. Okay. Let S be the event that a tomato plant was sprayed with insecticide. Let A be the event that a tomato plant has aphids. So we need to find the probability of, we'll say S, sprayed with insecticide. And that's going to be 52 over 80. 52 over 80. And let's see, that reduces to 13/20. Right? Now, probability of aphids. What's the probability of aphids? And let's see, has aphids, that's going to be 26 over 80. And let's see, that's going to be 13 over 40, right? And let's see, the probability of S times the probability of A, that's going to be 13 40ths times, 13, probably, let me put it in the right order here. 13 over 20 times 13 over 40. And I get 169 over 800, which is about 21%. Okay. And let's see. Now the probability of spray intersection aphids. Okay. Spray intersection, spray with it and has aphids, that's going to be 12 over 80. 12 over 80. I got that right there. 12 over 80, which is about 3 over 20, which is, I think, 15% here. 15%. So the probability of S intersection A does not equal the probability of S times the probability of A. So that tells us the events are not independent. Okay. A student wants to know if right-handed people are more or less likely to play a musical instrument than left-handed people. The student collects data from 250 people, as shown in the two-way frequency table. Determine whether being right-handed and playing a musical instrument are independent events. Okay. So let's see. The probability of being right-handed. Okay. So that was 220 over 250. 220 over 250. And it's going to be 22 over 25. 22 over 25. The probability of playing an instrument. Probability of playing an instrument. Let's see. Plays a musical instrument. That's going to be 50 over 250. And that's going to be 1/5. All right. Now let's see here. Probability of R times the probability of I. That's going to be 22 over 25 times 1 over 5. And that equals 22 over 125. All right. Let's see. Now let's find the probability. Find the probability of right-handed intersection plays an instrument. Okay. Right-handed and plays a musical instrument. That's going to be 44. So that's 44 over 250, which is 22 over 125. So let's see. The probability of being right-handed and playing an instrument or intersection and playing is, let's see here. That equals, because this is 125, 22 over, that's 22 over, that equals the probability of being right-handed times the probability of playing an instrument. So these events are independent. These events are independent. So determine whether being right-handed and playing an instrument, yes, they are independent. We answered the question. 10. What are the ways that you can show that two events A and B are independent? Okay, so one way is the probability of A given B equals the probability of A. That shows that the two events are independent. Okay. Another way, the probability of A and B equals the probability of A times the probability of B. How can you find the probability that two independent events, A and B, both occur? Multiply probability of A and the probability of B. Give an example of two independent events and explain why they are independent. One of the easiest ones is flipping a coin. Flipping a coin. All right. The result of the first flip has no effect on the result of the second flip. The result of the first flip has no effect on the result of the second flip. All right, folks, great lesson. Appreciate your time. I will see you tomorrow in class.